Thanks, Jeff. Hi everyone. I'm an experimentalist at Schoelkopf Lab, and today I'm excited to talk about our experimental proposal on error-detectable two-qubit gates for bosonic qubits. And throughout my talk, I would like to convince you that the concept of fault tolerance can help designing better two-qubit gates for erasure qubits. So what is the error-detected gate? So error-detected gate is a gate that has a built-in check mechanism that tells whether the gate succeeded or not. Typically, the infidelity of a physical gate is limited by the duration of the gate and the lifetime of your qubit, which we quote their ratio as P physical. When we have an ability to check an error during the gate, we will gain more information about the final state. For example, if an error is flagged, we learn that the resulting state is corrupted. On the other hand, if all the gates were passed, we can be confident about the output state that it's not corrupted. To put these in quantitative terms, the infidelity of the successful gate becomes quadratic to P physical when the detection can catch up to one error. This is because the gate needs to experience double decays in order to incorrectly pass the check. Of course, this comes at a price of needing to throw away failed shots, but overall, our knowledge about the output state improves by adding error detection to each gate. We think that the first-order protection against hardware errors can be a shortcut to reducing hardware overhead in 2D codes, such as surface codes. We know that the distance required for the surface code reduces dramatically if we surpass the error correcting threshold. However, it is very daunting to improve the lifetime of a qubit or improve the gate speed by a factor of 10 or 100 from the state of the art. What hardware error detection provides us is squaring of the physical error rate without needing to improve our hardware. Moreover, in the case that the lifetime improves by a factor of 10, we might expect that the error-detected gate has a potential of improving the Pauli error rate by a factor of 100 because of this squaring effect. In case we detect an error during a gate, we'll report it as an erasure and we'll feed the information into the decoder. The neat thing about the erasure rate, as Shruti mentioned, was that you only need half the distance than the usual Pauli error rate, and the threshold for the erasure rate is much higher than the Pauli errors. This provides us with a similar quadratic scaling in P's physical to surpass the error correcting threshold with current technology. So now the question is how to make our error detectable gates at the physical layer. This brings us to the outline of my talk. So first part of my talk, I will explain how to make an error detected gate hardware efficiently. Specifically, I will talk about what is the suitable hardware to realize the error-detected gate and introduce the concept of fault tolerance at the hardware level in order to make error-detectable gates. Secondly, I will apply those concepts and propose an error-detectable two-qubit gate for superconducting circuits. So typically, when we encode a qubit in the first, we use the first two levels of a quantum system. And the P physical scaled linearly to the relaxation time, which we call T1, and also the dephasing time, which we call it as T5. When tackling with these errors, our strategy is to embed an internal code in the hardware that allows error detection, and instead of scaling up with more qubits. The easy way to tackle relaxation is to add buffer level and detect the decay by measuring the middle state. Since you need to decay twice to introduce the logical error, the T1 portion of the Pauli error rate can be squared. It would be ideal to find a way to detect dephasing error as well, but you can also think about looking out for hardware that has intrinsic small dephasing error rate. This leads to our motivation to use the harmonic oscillator as a carrier of quantum information. So first, a harmonic oscillator has infinite levels in one mode, which can be used as buffer levels in this error-detected gates. Secondly, there is an intrinsic noise bias between the dephasing rate and the decay rate, so we can make use of that bias. Lastly, the single photon loss is generally longer than the typical transmon superconducting qubits, and we expect these lifetime to benefit us in the gate fidelity. In the superconducting system, we can realize these harmonic oscillator by using the standing mode in a stub cavity like Akshay mentioned. And there is an improvement in the T1 with using new materials or new designs. Also, we have making an effort into making this 2D using a hairpin resonator, and it has shown a competitive lifetime compared to the 3D cavity architecture. However, the harmonic oscillator itself doesn't provide us with a universal gate set. We need to introduce some form of nonlinearity, and we use qubit for this. We use a transmon, which is a type of superconducting qubit used as a physical qubit in the Google or IBM architecture. But for our architecture, we use this as an ancilla to introduce nonlinearity to the bosonic modes. We can couple those bosonic mode and the transmon by dispersive coupling, which is in the qubit language, ZZ coupling between a qubit and a boson. Surprisingly, this is enough resource for nonlinearity to make a general bosonic state and also do the universal gate sets. And the typical circuit involves a unitary evolution between those two modes, and also you can have a classical feedback dependent on the measurement, mid-circuit measurement result of the transmon qubit. And this platform has enabled the implementation of multiple error-correctable qubits, such as CAT codes or binomial codes or GKP codes, and each of them broke even at a lifetime. Now that we reviewed which platform to work on, let's look at how to ensure error detectability in gates at the hardware level. So before we get into details, let's briefly return to the bigger picture. So when we want to create a bosonic quantum computer with superconducting circuits, we consider laying out harmonic oscillators in two-dimensional arrays coupled by boson-boson interaction. We also couple transmon qubits periodically in order to introduce nonlinearity to the bosonic systems. When concatenating these bosonic logical qubits, it is crucial to consider the error propagation property during the gate we used in order to make gates. So there is some questions we need to answer in order to ensure the error propagation property, and which are like, how should we protect the errors from the transmon into the bosons? Because typically the transmon error rates are larger than the bosonic error rate. And also secondly, how should we ensure the error propagation property or fault tolerance between the boson-boson interaction? Because what we are doing is effectively embedding a logical qubit in the boson, which means that we need some kind of notion of fault tolerance between the gates between those hardware-efficient logical qubit. So what are the challenges in considering fault tolerance at the physical level? So in the conventional fault tolerance circuit, the gates are assumed to be instantaneous. Also, the gates and the error types can be represented by Pauli operators, which allows easier analysis in the error propagation by simple commutation relations. On the other hand, when we work at the hardware level, we have to think that the gates are continuous and it has a finite duration of time. That means that the error can happen anytime at the Hamiltonian evolution, and we have to accommodate those flexibility in order to think about the fault tolerance. These questions have been asked in the field of bosonic quantum error correction past 5 years, or more than that. And our work contributes to extend the condition that has been in the field, and for the ensuring fault tolerance between a boson-boson interaction. So how should we think about the fault tolerance at the hardware level? I will introduce a canonical approach taking the field. So at the hardware level, we can consider the commutator between the Hamiltonian and the error generating. Yeah. This allows us the analysis of the error propagation during the gate in comparison to considering the commutator with the unitary gates in the gate-based model. The simplest and the strongest condition for the fault-tolerant Hamiltonian is so-called error-transparent conditions, where if the error and the Hamiltonian commutes together, you can commute. You can think that the error doesn't propagate to the other rail. So for example, the coupling we use to couple a transmon and a qubit, which is a dispersed interaction, has this property. So when the dephasing happens on the transmon, it will commute with this Hamiltonian. So that means that dephasing error on the transmon doesn't propagate into the abosonic mode. On the other hand, the decay operator, which is like T1-like operator, doesn't commute with the dispersive interaction, which means that it can propagate to the central system, a bosonic system, and that will create a dephasing in the bosonic qubit. And this defeats the purpose of using harmonic oscillator as a intrinsic noise bias memory, because we thought that the bosonic mode has much lower dephasing rate, but by adding transmon, we'll create this noise bias not present. However, we can get around this by using 3 levels of a transmon and treat the first excited state as the flag level. As long as we can perform the high fidelity measurement on the flag level, we are effectively error transparent to the decay error to first order by post-selection. If we use the chi-matching technique that actually showed in the previous talk, we can keep the state without throwing it away, achieving full error transparency. Although the error transparency condition is safest way to ensure fault tolerance, at the heart of, the error transparent condition was too strict that there is not much Hamiltonian that follows this commutation relation. So our contribution was to introduce a looser condition that includes more Hamiltonians and identifying an error-detectable Hamiltonian for boson-boson interaction. So the choice of our boson-boson interaction is so-called the beam splitter interaction. In other fields, maybe this is called as an exchange interaction, but it basically does is that it swaps the photons between 2 bosons. And we can realize this in circuit by using a coupler made by nonlinear elements like transmons or squids. And we apply microwave pump to change the mixing rate, and we can make arbitrary mixing between the 2 modes. Sorry. So the reason why we use this interaction is because it has nice commutation relation. It doesn't have error transparency, meaning that it doesn't commute, but it can produce a commutator that is also a photon loss, which means that it is closed within error-detectable error sets. So we call this error closure condition, but let's see how a photon loss commutes with this beam splitter Hamiltonian. So when we think about a random error happening during the gate, what it means is that you can divide the evolution in 3 parts. The first part is the beam splitter before the photon loss. The second part is the photon loss at the random timing. And third part is the photon beam splitter evolution after the photon loss. So you can analyze this by thinking about applying a unitary operator based on this beam splitter interaction to the state. And you can find that the resulting error operator after the gate look like the Heisenberg representation of a photon loss after some unitary beam splitter interaction. The good thing about this Heisenberg representation is that all the terms, all the nested commutators produces photon loss, which means that any photon loss during the gate can be commuted through the end, and assume it as a superposition of photon loss. And because we encode our bosonic logical qubit by encoding such that it can detect photon loss, we are effectively can find a photon loss after the gate, even though the photon loss happened during the gate. So one experimental example in our lab is that my colleague ran a randomized benchmarking on using this beam splitter gate on the dual subspace and realized a swap gate fidelity of 99.92%. Furthermore, you can do the erasure check, and you can post-select away the errors that experience the photon loss, and the error-detected gate fidelity was 99.98%. So although this is a single cubic gate in the dual-L subspace, this demonstrates how well we can swap a photon between two bosonic modes in the lab. So with these ingredients, let's see how to create error-detectable entangling gates on bosonic qubits in superconducting circuits. Here are the ingredients of error-detected gates in superconducting circuits. So the left diagram shows like typical setup in our hardware, and the circles represent the bosonic modes, and the green cross represents the transmon qubit. The beam splitter is the way that we couple the two bosons, and it satisfies the error closure condition for photon losses. And also, when we couple the qubit and the ancilla qubit and the boson, we use dispersive interaction, which satisfies error transparency condition for the dephasing. Lastly, we use the three-level ancilla in order to catch the decay error in the transmon ancilla. So let's look at the dispersive interaction, how we can use dispersive interaction to introduce nonlinearity to the boson. So since the dispersive interaction is like a C-phase gate between a boson and a transmon, the photon number information can be mapped to the phase of the transmon qubit. So by applying a phase estimation, you can map the photon number parity of bosonic mode to a binary output of the transmon. By reducing the time of the evolution to half, which is taking the square root of the parity, you can map mod4 superparity to the ancilla. The superparity acts as a logical Z operator for rotation symmetric codes such as cat code or binomial code or dual qubit. So in effective, the dispersion interaction with some specific duration makes a control Z operation between ancilla qubit and the logical bosonic qubits. Similarly, you can map the joint superparity of two bosons to the ancilla by activating beam splitter interaction during the disperse interaction. Since the beam splitter interaction swaps the boson with a high repetition rate, it effectively makes both mode coupled to the ancilla, which allows the ancilla to observe the joint photon number. Similarly, similar to the single mode superparity mapping, for the rotation symmetric codes, the joint superparity mapping creates a control ZZ between a transmon and two modes. Importantly, this control ZZ operation will be a crucial component for arbitrary ZZ gate rotation gate. So we know from the textbooks that by combining control ZZ gate and the ancilla rotations, we can create arbitrary ZZ rotations. Although this is not an error-correctable gate construction, it is sufficient to detect errors during the gate. So I will go through how the error detection works from the ancilla errors. So errors in the ancilla qubit can be flagged by using these three-level ancilla. And the final state of the ancilla will diagnose what kind of error happened during the circuit. So if you measure the ancilla in the E state at the end, you know that the ancilla decay happened. And also, if you measure the F state, you know that the ancilla made a dephasing. That the gate will be only accepted when the ancilla ends up at the ground state. Also, the loss in the bosonic modes can be detected by erasure check after each gate. So in the dual encoding, we can implement the DZ rotation by the following circuit. Although the dual encoding uses 2 modes per qubit, we don't have to make a full body interaction, and we can show that the only coupling 2 modes will be sufficient to make a DZ gate on the dual qubits. So how can we test the error detectability, at least in the numerical simulation? So as I alluded in the beginning, the total error is a sum of single error and double errors, and so on. When we don't detect the error, the total error scales linearly to the lifetime, whereas the error-detected infidelity scales quadratically to the lifetime. We can estimate the gate fidelity by using a master equation simulation, taking realistic gate time and errors into account. In the simulation, we can sweep the lifetime and test the hypothesis by a hypothesis of quadratic scaling in error-detected gate. In the right plot, we swept the dephasing time and confirmed the linear dependence of error-detected error scaling, which we call the p-fail in the red line. On the other hand, the blue line shows the error detected fidelity, which shows quadratic dependence in dephasing. We also incorporated the readout error because at the end of the day, the error detection relies on the good readout fidelity. And these square and also triangle markers will show like the effect of the readout errors on these error detected gates. The same trend can be seen in the unsealed decay and also photon loss in decay. And we have confirmed that all these dominant errors in the hardware can be suppressed to first order. And the gate speed depends on the typical gate speeds depend on this dispersed interaction speed, which is about 1 microsecond. And with modest transmon lifetime of like a few hundred microseconds, we estimated that error detected fidelity would approach 4 nines. And we are currently working on implementing this in our lab. So in conclusion, I have introduced that bosons might be a great platform to engineer erasure qubits, and showing a recipe to make error-detectable 2-qubit gates in qubits by considering a fault-tolerant condition. Lastly, I showed in numerical simulation that it might be possible to make a fidelity error-detectable 2-qubit gate in the current hardware lifetimes. Lastly, the open question I'm interested in for future studies is to explore a good qubit based on the fault-tolerant condition instead of starting with a qubit to make a better gates. With that, I would like to end my talk and happy to take any questions. Thank you.
Thank you. I'll open the floor for questions. I will start with one again. So what would it take for you to do mid-circuit measurements of the photon loss errors?
Oh, yes, thanks. So we use one of those joint parity measurements in order to do the erasure check. So we take one part of the gate. This control ZZL will effectively do the erasure check. So we can add this after the gate application.
I see. And then to be able to get the information out in the middle of the circuit, you would just need to read out the transpond.
Yeah, exactly.
I see. And then reset it. So we have a question from online. It's, can you comment on the scalability of error detection given that the protocol relies on post-selection? Is there a way to implement through QND? Which actually
Implement the QND?
Implement through QND, which I think is actually the same as my question.
Yes, sorry, I think it wasn't clear. So the joint parity measurement is QND to the bosonic state. So measuring them doesn't collapse the qubit state in the bosonic modes. And in terms of the scalability, I think there's 2 routes. One is using this error-detected gates for like NISC circuit, which is like you have a short depth circuit where you can allow throwing away shots with very short depths, and then you will post-select on shots that have like all being successful. And the other route is to embed this error-detected gate as a physical layer and make it like make an upper layer decode these erasure errors and to make it fault-tolerant.
Thanks for this very inspiring talk. I have 2 specific, very technical questions. So I realized in your slides you assume the gate error to be the ratio of gate time and your qubit coherence time. So can you please elaborate more on your motivation why you didn't consider the control imperfection during in practice? Because I think like for transmon qubit it takes it also a very large portion in your error budget.
Thanks for the question. Yes, that's a good point. We assume that the control errors I mean, we were looking at only on the random errors that pollutes that kind of sets the upper lower limit, the upper limit of the error happen in the bosonic systems. That's why we only choose the random errors. But also the control errors are, I would say it's not that difficult to mitigate. In the case for us, for the bosonic qubits specifically, because the gates are relatively longer than the transmon qubits, which allows us not being able to do like non-adiabatic transition or very aggressive gate control. So that was the reason why we didn't think about the control errors as dominant errors. And also, I would like to comment on the other source of errors, which kind of shown in this middle plot, but like there's also a readout error that can limit the first order protection. So in the end, it is like the total sum of the second order random error, and also the error that comes from the readout error, and then that will eventually makes it to first order error. But the point is that you get the error detected gate fidelity improvement by a factor of the readout fidelity. So that's those are, I think, the two main sources there we can think of.
Yeah. So the other question is, so also in this slide you said you assume the readout error to be 0%. So does you only consider the assignment error, or you also consider the readout duration, where you also have your qubit suffered decoherence during this time?
Yes, I think I took a typical number from the superconducting qubits, but it depends on the duration of the readout, because most of the readout error comes from the decay of the transmon during the readout. So if you have your readout to be faster, that means that you have less likely to experience T1 errors, and that could be another room for improvement in the system.
So do you have any feeling about the typical readout duration for the current state of art?
So in our lab, it's more or less like a few hundred nanoseconds or 1 microseconds. But for the state of the art, some groups have shown like 100 nanoseconds or 50 nanoseconds level of the readout errors, readout duration. Yes.
Yeah, all clear. Thanks.
Thank you.
Thank you for the talk. So by coupling your 2-qubit gate on the bosonic modes to a ancilla qubit transmon, how do you handle any considerations that must change for the architectural connectivity?
Could you? I couldn't understand what the essence of the question. Sorry.
So I asked, how do you handle any considerations for this hardware connectivity constraint that you're now requiring that the hardware between any two bosonic modes needs to connect to a transmon?
Oh, I see. Okay. So first of all, you connect harmonic oscillators in 2D, and then I think you need like one additional arm for like a cube, like for a boson, like in every 2 boson or something. And that will increase the connectivity per bosonic mode on average. But I think the scalability, in terms of like the complexity of like expanding this to 2D, I think it's not an issue, because basically adding a transmon, like you have a room, like you can have 5 arms from 1 boson, for instance, and I think it's not an issue.
What kind of graph shape would you have in mind for this?
Okay, sure. So maybe I don't have a backup slide for this, but maybe this is one example that I think this is the one example of the layout that this architecture might work. it doesn't couple like a transmon to each bosonic mode, but it couples in like once in every two. And as long as we can couple the bosonic modes in 2D, I think it is possible to put additional transmon in each bosonic mode.
Okay, thank you very much.
Thanks for the nice talk. A couple of years ago, there was a lot of discussion about how as you connect more cavities, there are seams that come in and that starts to affect the quality of the mode. You show some very nice results of just single cavities now having above 25 milliseconds or possibly even longer. Could you comment on some of the progress in terms of as we connect more of these cavities, whether there are subtleties related to the boundaries, how good things are if you have a lot of cavities, things like that?
Mm-hmm. That's a great question. So I think in terms of the repeatability, I think so. The second. So the second figure here is not in our lab. It's from the different lab, which addressed your concern about having a seam loss, where you kind of make the seam of the cavity as small as possible, and that has also there's other cavities that have more lifetime that address these issues, and that's a very like hard way to, how do I say? I think it's a matter of the trade-off between like scalability and this lifetime of each mode. I mean, the longest lifetime seen in this field is about 2 seconds, which has very strict seam loss engineering. But on the other hand, you can't like have this many in like one room or one fridge. On the other hand, the stub cavity we are using is much shorter than 1 second, but at the same time, the repeatability of making this is fairly good in a sense that it has a seam loss. We don't address covering the seam in this architecture, but it has 1 millisecond constantly, which means that, I mean, if we want to scale, I think we would like to move in that like a boson cavity that has like enough lifetime, but also repeatable in scaling.
So let's thank Takahiro and all our speakers again in this session.
Thanks, Jeff. Thanks.